I will present weight erosion, a novel update aggregation scheme for personalized collaborative machine learning. Don't worry about the technical jargon in the title, as I will explain each part of it before diving into the scheme itself. Let's start with collaborative machine learning. It allows several agents, such as hospitals, to come together and train a machine learning model on the union of their individual datasets without ever copying and sharing any of the data. As such, it can be a powerful tool in global health research to gain statistical insights early on in an epidemic while maintaining full control over the privacy of patient data. There are two prominent paradigms of collaborative learning which differ in the shape of the communication network. In federated learning, individual participants communicate bilaterally with a central server. These participants are any entities that hold data. They can be institutions such as hospitals or individual mobile devices, etc. In contrast, decentralized learning methods rely on each participant sending messages around to their neighbors, or in other words, to a subset of the other participants. The definition of a participant is the same as for federated learning. Importantly, it is possible to learn exactly the same model as with a centralized data set, all the while ensuring that individual messages do not compromise any individual datum points, though that is not trivial, admittedly. In fact, any gradient-based method can be implemented in a federated and/or decentralized way. This means that collaborative learning works for simple models such as linear regression and logistic classification, as well as for terribly complex deep convolutional neural networks. For the remainder of this presentation, I'll focus on federated learning because decentralized learning is still a very new research topic. I will assume that the participants are individual hospitals, and to make things complicated, I'll call them agents from here on out. An issue that often arises in collaborative machine learning is that the data is not identically distributed across agents. For instance, if one model is trained using the data from two hospitals located on different continents, it might not perform well for either of them. On the other hand, if the agents don't collaborate, the dataset locally available to each of them might be too small to generalize well. And that gives rise to the task of model personalization, where the agents collaborate to train a plurality of personalized models, maybe one per agent or per cluster. If one of the agents wishes to train a particular model that performs well on their own dataset, weight erosion helps that requesting agent leverage the more useful agents without suffering from the less useful ones. So, what are we proposing? As suggested by the title, weight erosion is an update aggregation scheme. This means that it intervenes after the server has received a locally computed model update from each agent and must combine these individual updates to update the global model with. The simplest such aggregation scheme is federated averaging, where the individual updates are simply averaged. Weight erosion is inspired by a recent publication in which, at each round, the server takes the individual updates it has received from the agents and computes pairwise Euclidean distances between these updates. These distances are used for different purposes there, but in weight erosion they serve to pick agents whose updates are somewhat aligned with those of the requesting agent. And this makes sense, right? At first glance, if two datasets are similar, you'd expect to get similar gradients back after all. To illustrate this, let's say you're agent 0, and this is the empirical loss function on your dataset, represented here by its level sets. Now here are two other agents, 1 and 2, with their own datasets and the level sets of their corresponding loss functions. In this example, we see that the empirical loss functions of agents 0 and 1 have a lot in common, so much that one could explain the difference as a mere sampling phenomenon. Clearly, both datasets should be used in training. The same can't be said for Agent 2, whose empirical loss function hints at an entirely different data distribution. Thus, we can expect that if each agent computes a mini-batch gradient, then the gradients of agent 0 and agent 1 will be much less far apart than the gradients of agent 0 and agent 2. This difference is measured by their Euclidean distance, here between G0 and G1, and between agent 1 and 2 here. However, these distances actually depend on several influences. For starters, they depend on random chance, since each agent randomly samples a mini-batch. There is no guarantee, after all, that the gradients computed from the next mini-batch will point in the same direction. Critically, though, these level sets also depend on how well the model is already performing. To illustrate this, imagine that agent 0 and agent 1 have two fairly small data sets that are drawn from the same underlying distribution. As the trained model is smack in between the two local minima, well, this is probably where you want to be, right? This is the most reasonable model to pick if you know that both agents sample from the same distribution. But at that point, the gradients actually point in opposing directions. They're not aligned at all. Those sound like issues, right? But how do we solve them? Well, we give each agent a weight and compute a weighted average of the various agents' gradients. So weighted federated averaging, if you will. Let's call these weights alpha and set them to 1 in the initial round. The notation reads, this is the weight at round 0 for agent I. At each round, denoted R, that weight then decreases by an amount delta alpha, which is proportional to the distance between the two gradients. You might notice in the last formula that this distance is normalized with respect to the size, or precisely the 2 norm of the gradient computed by the requesting user. Remember that is the user who wanted to train a personalized model in the first place. You'll also notice in the previous formula that the weights are capped at 0. They can't be negative, and that's because we don't believe that it is useful to include negative contributions by any agents. Instead, agents like agent 2 are simply quickly disregarded because their weight reaches 0, while agents like agent 1 remain relevant for longer. We tested the weight erosion scheme on an application study using the Titanic dataset as well as Ebola data. Since this was done before our data access request was granted, we were limited to the data collected by Annie and her colleagues in Sierra Leone in 2014 and 2015. Honestly, we found more interesting insights from the Titanic study, but I couldn't just not talk about the application on Ebola data. I think, though, that a big advantage of the Titanic dataset was simply the fact that it contained more than twice as many samples. We trained a logistic classification model to predict Ebola diagnosis based on the features identified as most predictive by Annie in her 2017 publication. To make sure that the data in this application study is non-identically distributed across agents, we split the patients into age groups. Each agent was given the data corresponding to one such age group. Finally, we simulated the collaborative training process on a single device. We repeated the simulation 3 times, each time with a different agent as requesting user. Shown in figure 1 here is the accuracy on the requesting user's test set, for the case where the patients are strictly separated into age groups. We compared the model trained with weight erosion, shown in blue, to a model trained exclusively on the requesting user's training set, shown in black, as well as to another model trained with federated averaging. This one's in green. Shown in red dashed lines is the baseline accuracy obtained with a stupid model that predicts the same value for all patients. Finally, the dotted lines represent the weight of each agent as it evolves over time. The first thing we noticed was that federated averaging performs very poorly in this setting where each agent has a fairly unique data set. The results also suggest that the weight erosion scheme can, under certain circumstances, significantly outperform local training by making more data available to the requesting user, even when federated averaging fails. This is what we see for agent 1 here. Meanwhile, in this example, weight erosion always works at least as well as local training. We also took a peek at the model weights for the models that achieved a high classification accuracy. We saw that the strongest weights were associated with having been in quarantine because of a suspected contact with another Ebola patient and arriving at the treatment center with conjunctivitis. Finally, we note that the baseline accuracy is noticeably different for the age group of 21 to 40-year-olds. This was not intended, as we split the patients into age groups, hoping to create 3 datasets of roughly equal size with a systematic difference in how the symptoms relate to the diagnosis. However, the red dashed lines show that the proportion of positive diagnoses among the patients aged 21 to 40 years old was much lower than in the other age groups. Of course, this could mean a wide range of things, that people in that age group are less likely to be infected with the Ebola virus, or that they're less likely to be referred to the Ebola treatment center, or maybe that a person within that age group who was not infected with Ebola was more likely to be referred to the treatment center because of some other affliction. This is the kind of question we couldn't really answer without looking at other data sets. In conclusion, we designed a new update aggregation scheme for collaborative machine learning, wherein data from several agents are used selectively to learn one personalized model for the agent who requested a model to be trained in the first place. An application case study shows that in a case where federated averaging struggles due to data being non-identically split across agents, the weight erosion scheme can outperform a locally trained model. It seems to strike a compromise between the transfer error of a globally trained model and the generalization error of a locally trained one. In particular, in this application study, weight erosion is always at least as good as the other options. Some of the logical next steps include benchmarking weight erosion against some of the established model personalization methods. Model personalization also doesn't seem to be implemented in most of the existing federated learning frameworks yet, so that's another promising avenue. Personally, I'm also working on providing confidence measures such as confidence intervals, for example, for the predictions of personalized collaborative machine learning models. Finally, let me end by proposing an alternative, complementary interpretation of what it can mean to use machine learning, or more broadly, artificial intelligence, for global health. Indeed, recent events during the pandemic have been a stark reminder that global health outcomes can hinge as much on how well-informed and how collaborative the public is, as on the resources available to the healthcare system and to medical research. Public opinion and cooperation, however, have been severely affected by the impressive spread of dangerous disinformation and conspiracy theories like anti-vax and QAnon, much of it on social media. We get to see this repeating pattern, where the recommender systems of major social media platforms massively promote conspiracy theories, until the platform's management steps in and promises to ban the specific content related to that. All the while, their recommender system continues to specifically target vulnerable users with harmful disinformation. And while we mostly hear about these things in the US, the recommender systems work in the same way across the globe. We just don't take notice of what they do in lower and middle income countries. So, in the face of this, AI for global health can and should also mean designing artificial intelligence in a way that is beneficial to global health goals rather than actively undermining them. And let me also state how much potential there is to use those same recommender systems to spread good information through engaging content and maybe with some political pressure on the social media companies to actively promote it.